A very good morning to all of you, and I hope everybody has enjoyed during winters. And of course, our winters were extremely hard. The temperature went down uh, nearly to -10, -11 degrees Celsius. And we still hope that maybe there is some good quantum of snowfall, because this year the snowfall was it was for a very short span of time. It didn't extend to over a long period of time. So let's hope that by the will of God that we will have snowfall in coming days, uh, and and I hope all of you have enjoyed at your homes and during the vacation that we have encountered for the last 40 to 50 days. So today I'll be talking about Stern-Gerlac experiment. This is the title in our syllabus, and I'll be talking about this Stern-Gerlac experiment. And probably I think we have already covered the course on hydrogen atom, and we understand that when we discuss the problem of hydrogen atom in spherical polar coordinates, it gives us quantum numbers, it gives us principal quantum number, it gives us orbital quantum number, and it certainly gives us magnetic quantum number, but it does not give us any information about the spin that an electron can have while being present inside the hydrogen atom, surrounding the nucleus of the hydrogen atom. So, in fact, this experiment does not directly lead to the confirmation of the existence of spin of an electron, but the same experiment could be traversed, the same experiment could be taken on to understand the existence of intrinsic spin of an electron. Now, this is a pretty simple kind of experiment that was conducted by Stern and Gerlac, and this experiment primarily gives us the measure of the quantization of angular momentum. And what does this experiment look like is that you have something that evaporates neutral silver atoms. So you have silver atoms, and these probably you can evaporate these silver atoms using a furnace, using an oven. So you have an oven, and this oven produces neutral silver atoms. And then what we do is we make use of collimators. And we understand why we use collimators. We use collimators to obtain a fine beam. So what we have is we have collimators. And using collimators, we can have the fine beam of silver atoms. Now, what's most important point at this moment is that you produce these neutral silver atoms, and then you collimate the beam of these silver atoms, and you are not looking at these atoms, because I believe that Stern-Gerlac experiment is another way to understand the working of a quantum computer, the forming of a quantum computer, the basic principles that we have in designing a quantum computer, where you can execute an operation using the basic laws of quantum mechanics. And probably when you have these silver atoms, moving through these collimators, you are not intervening with these silver atoms. So if you are not intervening with these silver atoms, these atoms must have some kind of superposition existing between all of the atoms, the millions of atoms that are passing through these collimators. Now, what they did, what Stern and Gerlac did, they projected this beam of silver atoms on a non-uniform magnetic field. So you have a magnet, say this is North Pole and this is the South Pole, and we call this basically the pole magnet. Well, you can have a non-uniform magnetic field, and this magnetic field is its intensity is not same. Its intensity goes on varying from point to point. And then after this, what we have is we have a screen. You may call this a screen as a photographic plate, or you can have a real screen that can sense the presence of silver atoms. So these silver atoms are subjected to this non-uniform magnetic field. So what we have in this experiment, the basic things what we have is we have something that can produce the silver atoms. Then we make use of collimators, 2 or more than 2 collimators, so that we have a fine beam of silver atoms. And then after that, what we have is we make use of a non-uniform magnetic field, and then we have a screen, and or you may call it a photographic plate. So what we observe, what these people observed when they performed this experiment, what they observed is that they could find the beam that we have. The beam gives it hits the two points on the screen. And probably, if we think about the silver atoms as atoms, an atom can be assumed as a tiny magnet. We understand it from the basic physics point of view. So you have the external magnetic field, and you are applying this external magnetic field on the tiny magnets. So these silver atoms, the neutral silver atoms, they can be treated as tiny magnets. So what we expect in the normal way when we perform this kind of experiment, what we expect is that the whole of this screen should be shot by these silver atoms. Every point of this screen should be shot by these silver atoms. But that's not the case. What we observe in the experiment is different from that of what we are predicting from classical point of view. So what we are seeing here is the two portions, and between the two portions we have the distance. And between the two portions, the silver atoms do not hit the screen at all. Now, what does it mean literally? What's going on? So every time an experiment is performed, you perform an experiment, you get some result on the screen. Now, what you try to explain why this kind of thing is coming on the screen. So this is the job, that you have to explain that why you are getting two spots being hit by the silver atoms on the screen, but not on the other hand, as the whole of the screen is being shot by these silver atoms. So this is the basic sketch of the experimental setup that has been used by Stern and Gerlac, and this experiment being the basis of the existence of the intrinsic spin of an electron. Obviously, here we are taking into consideration the silver atom. So atom as a whole is assumed to be a tiny magnet. Now, the two things are happening here. If we think about this experiment, you have a stage where silver atoms are moving in these collimators, but you are not trying to measure them. So when you are not trying to measure them, within the framework of quantum mechanics, these silver atoms will have the superposition. They will have the superposition. They will have all possible orientations that you expect on the screen of the Stern-Gerlac experiment. But once these silver atoms come close to this non-uniform magnetic field that we have, what we observe is that there is fragmentation of these millions of silver atoms, and some of the silver atoms will hit the upper part of the screen, and some of the silver atoms will hit the lower part of the screen. So here, applying the magnetic field, applying the non-uniform magnetic field on these atoms is basically, you are basically collapsing the wave function because you are making the measurement on these silver atoms. But before the measurement, they will have all possibilities. All of these silver atoms will be in superposition. And once there is an act of measurement that's being shot on these silver atoms, they behave in some specific way where we could see those two important positions on the screen, and leading us to have some kind of quantization that is linked with these silver atoms once you subject these silver atoms to the external magnetic field. Now, if we take a qualitative way of understanding this experiment, what we do is we have the silver atoms, and all of these silver atoms, they are tiny magnets, and when you apply the non-uniform magnetic field, these atoms will experience deflections. They'll be deflected, and the deflection will depend on the orientation of the silver atoms. So what probably comes in our mind immediately is that you could have two possible orientations when you are applying an external magnetic field on these silver atoms. So you will have orientation, say for example, for the sake of argument, you will have an orientation clockwise and you will have an orientation anti-clockwise. Now the silver atoms which have clockwise orientation, they might be deflected to the down point, and the atoms whose orientation is clockwise, they might be deflected on the spot B, and we can find out the directions of the deflection of these atoms. Now, if we subject the same problem to a mathematical treatment and try to understand this kind of deflection, and this deflection is leading all of these silver atoms to hit the screen at the 2 points. Now, another important question that arises in our mind is that why Stern and Gerlac, why they use the non-uniform magnetic field while performing this kind of experiment. And if we have to go with a plausible explanation, suppose I make use of the uniform magnetic field, and on applying the uniform magnetic field, you will have the torque. You have a magnet in an external magnetic field, and if this magnetic field that you are applying on these silver atoms is a uniform magnetic field, then maybe most of the atoms will experience the torque, and they will not hit the screen. They might scroll because of the torque that these atomic dipoles may experience. So that could be one of the reasons that why we are not using the uniform magnetic field, because if we use the uniform magnetic field, we will not obtain the the output as we expect, the output that gives us the quantization of angular momentum of these silver atoms, when you subject these silver atoms to an external magnetic field. Now, let's do a little bit of mathematics on this experiment and see how we can achieve some results based on this experiment. Now, if I go back to a magnetic dipole, and you have the magnetic dipole energy, and we have the potential energy. If I call this the potential energy, if I choose this potential energy as, say for example, V, then the potential energy of this dipole will be minus mu dot B, where this mu is what we call as magnetic moment. This is the magnetic moment of the atom. And B is the external magnetic field that you're applying on these silver atoms. So mu is my magnetic moment, and B is the magnetic field that we are applying on these atoms, and V gives us the potential energy. So as we understand from the basics of the physics, that if you have to calculate the force, and if you have to calculate the force, you can calculate the force in terms of the potential energy. Now, what's my problem? My problem is that I have, say, a silver atom, and this silver atom experiences a deflection. Okay, so if I tone my problem like this, that the motion, suppose this is my z direction in which I'm applying the magnetic field, and let's assume that these silver atoms are moving along y, and assuming this to be x. So what we have been doing here is we are applying the magnetic field in z direction, right? So let me write down that equation again. So what is V is minus mu dot B. So if I have to write down the force that this silver atom will experience, that will be minus del V. So the negative gradient of the potential energy will give us the measure of the force. And taking into consideration the dimensions, so I can think of writing F equals minus dou by dou Z of V. This is because I'm applying the magnetic field in the Z direction. Now, proceeding from here, what is V? I can use this V. So this is negative, so the force that I'm calculating here, that this force will be dou by dou Z of, instead of V, I'll be using mu B. Okay, so taking down this scalar product, assuming that theta is equal to, theta is 0, so taking this F, the measure of the F is the derivative of mu and B. Now we can proceed from here for the magnetic moment. So what is the magnetic moment? So these calculations are already done. We know this mu is the magnetic moment of an atom. So this is G, and this G is called Landy G splitting factor. And for silver atoms, the value of G is equal to 2. And then what we have E by 2m times J. Now what is J? J is the total angular momentum quantum number. J is the total angular momentum. So mu is the magnetic moment of the atom, so it is equal to G times E by 2m J. Where this G for neutral silver atoms, its value is equal to 2, and this E is the charge of the electron, and this 2 and m, it gives us the mass, and J is the total angular momentum. So we can think of using value of mu in this equation, the equation of force, right? So what we do for that we obtain this F is dou B by dou Z, and for mu we'll be using G E by 2m times J. Now what is this? J is the total angular momentum of the atom, of the silver atom, and from the analysis of the problem of hydrogen atom, we understand that this J is quantized, right? And when we apply the magnetic field, we have applied in this case the magnetic field along Z. So if we apply magnetic field along Z, then this J is MLH bar, where ML is the magnetic quantum number and H bar is the reduced Planck's constant. So F, so what we have here is F. So what will be F in our case? F in our case is, so F is, it is dou B by dou Z, and then you have G, and you have M, L, then you have H bar divided by 2M. Oh, that's right. So we can proceed from here. And the force, this is the force that these silver atoms are experiencing when you are applying a non-uniform magnetic field. And the force that it is experiencing is, so G is out, ML is out, dou B by dou Z, and then you have EH bar by 2M. Now the thing that you have in the brackets, this thing is called the Bohr magneton, and this E is the charge, H bar is the reduced Planck's constant, and is the mass. So mu B will give us EH bar by 2M. So F is GML mu B, and then you have dou B by dou Z. All right. Now, keeping in view that what's going on here is that your silver atoms, they're experiencing a force, and that force is given by this equation. And as I told you, that the value of this G is equal to 2, and this M, it has to be mg. It has to be the total magnetic quantum number. Here it has to be mg. Okay, it has to be mg because J is mg H bar. Fine. So the point is, what we understand from this equation is that you have a dependence of force. You have a dependence of force on some constants, and its dependence on the changing magnetic field. And can we predict anything from this equation? Can we predict anything from this equation? We can predict. What we can predict is from mj point of view. Now, if I have mj, we know it from basic spectroscopy that this mj will have 2j plus 1 values. And if I have to write down this silver atom, spectroscopically, we can write down it as 2s1 by 2. So what does this spectroscopic term mean? It means that the multiplicity of this atom, place C of this atom is equal to 2, that is this, and this S is referring us that the orbital quantum number is 0, and this 1 by 2 is the value of the J. So what we can have, Mj will have 2J plus 1 values. If I utilize this thing for silver atoms using J equal to 1 by 2, I would like to see what will be the value of Mj, and we better understand that Mj is the part of the force. So if you have two values of Mj, if you have a range of values of Mj, your force is also going to break into those parts. So what's going to happen here? What's going to happen here is, if I think of using 2 times, so what is J for this? It is 1 by 2, and then I have plus 1. So 2 and 2 will cancel. So you will have 2. Now this 2 will automatically lead us to understand, at least in this framework, that the force that will be experienced by these silver atoms, this force will split into 2 forces. And if it will split into 2 forces, that means there will be 2 different orientations, there will be 2 different deflections along which these silver atoms will be projected. And if they are projected into 2 different domains, you automatically come up to have on screen 2 spots which are being hit by these silver atoms. Now, to be precise here, Stern-Gerlach experiment does not directly give us the information about the intrinsic spin, magnetic spin, angular momentum of the electron, but this experiment certainly becomes the basis when we extend out this experiment to the further understanding. What we come up with is that electrons also have a spin, but that spin is not the classical spin. The spin that we think in terms of the classical physics, a spinning planet, a spinning sun, a spinning top, these are the classical ways of realizing the spin of the object. But when we talk about the spin of the microscopic particles like electrons, neutrons, protons, and all the fermions, basically, they have a spin, and the spin can be bifurcated into 2 categories, what we call as spin up and spin down. And to put a more insight into the Stern-Gerlach experiment, we can think of this Stern-Gerlach experiment as a basis of the modern development of the quantum computers. And as we all understand that a quantum computer is something that works on the principles, the basic principles of the quantum mechanics, where we have quantum bits, as we can treat them as an analog of the classical bits. We have, in classical world, we have zeros and ones as bits, but here in a quantum computer, what we have is we have quantum bits, and the projection, the theoretical projection of a quantum computer can be visualized using Stern-Gerlach experiment, because this experiment is automatically taking into account the superposition of the silver atoms, where you will have all possible orientations of the silver atoms. And once you make an act of measurement on these silver atoms, you are able to see 2 discrete spots being hit, which automatically leads to the collapse of the wave function of these silver atoms with which the non-uniform magnetic field is interacting, and leading us to find the result on the screen, where we can have two orientations of these silver atoms, which can further be translated into a base, as an experimental basis for the existence of intrinsic spin of fermions. So with this, I'd like to stop.